Complementary Events. Welcome, everyone. Today, we are going to explore a very important and practical concept in probability known as complementary events. Now, as you progress in your study of probability, you will often come across complex problems where calculating the probability of a specific event occurring directly can be quite difficult or even time-consuming. However, you might notice that it is often much simpler to calculate the probability of that event not happening instead. This clever shortcut, looking at the opposite side of the situation, is exactly what leads us to the concept of complementary events, which we will define and master in the upcoming slides. Understanding the concept. First, it is important to understand the relationship between an event and its complement. We describe them as two mutually exclusive outcomes that, when combined, cover every single possibility within an experiment. This means they cannot happen at the same time, but together, they leave no stone unturned. Nothing else can possibly occur outside of these two. To make this easier to work with, let's use some mathematical shorthand. If we define our primary event as E, then the event representing, not E, is what we call the complement of event E. In mathematical notation, we represent this complement by placing a small bar over the letter, written as E bar. If you find the notation a bit abstract, just think of it in the simplest terms possible. If E represents the event that something happens, then E bar represents the event that the exact same thing does not happen. As we will see in the next slide, this relationship is the key to using a very powerful formula for solving probability problems. Now that we've established why we look at the probability of things not happening, let's dive into what complementary events actually means. The mathematical relationship. Think about it this way. When we perform an experiment, an event E$ either happens or it simply does not happen. There is no third option. Because these two outcomes, the event and its complement, cover every single possibility, their combined probability must represent absolute certainty. In probability, certainty is always represented by the number $1. This gives us our fundamental formula for complementary events, which is the probability of event E$ plus the probability of E bar equals 1. Now, this equation is incredibly powerful because it allows us to rearrange it to find a missing value. If you know the probability of an event happening, but you need to find the probability of it not happening, you can use the first derived formula. The probability of E bar equals 1 minus the probability of event E$. Conversely, if you know the probability of the complement, you can find the probability of the original event by using the second formula. The probability of event E$ equals 1 minus the probability of E bar. Now that we have defined what a complement is in the previous slide, let's look at the mathematical relationship that ties these two together. Keep these formulas in mind, because in the next slide, we are going to apply them to a real-world scenario involving weather forecasting. Illustrative examples. Now that we have established the mathematical theory and the formula, let's put it into practice with our first real-world scenario. Take a look at this example regarding weather forecasting. Imagine you are watching the news, and the weather report states that the probability of rain tomorrow is 0.3. Based on this information, how can we determine the probability that it will not rain tomorrow? Let's walk through the solution step by step to ensure we are applying the concept of the complement correctly. First, we need to clearly identify our event, which we will use to call E in this case. Let E represent the event that it rains tomorrow. Second, we note our given value. From the report, we know that the probability of E, written as P of E, is equal to 0.3. Third, we identify the complement. As we discussed in the previous slides, the complement, which we denote as E bar, is simply the event that the original event does not occur. So, E bar represents the event that it does not rain tomorrow. Fourth, we apply the fundamental formula we learned earlier. To find the probability of the complement, we use the formula P of E bar equals 1 minus P of E. Fifth, we substitute our known value into the equation. This gives us P of E bar equals 1 minus 0.3. Finally, we perform the subtraction to find our result. 1 minus 0.3 leaves us with 0.7. Therefore, we can conclude that the probability that it will not rain tomorrow is 0.7. This simple calculation shows how powerful the complement rule is for finding unknown probabilities. Now, let's try a slightly different scenario involving a die roll in the next slide. Illustrative examples continued. Now that we've seen how this works with weather forecasting, let's look at a second example, this time using a classic probability scenario, rolling a die. The question asks, if we roll a fair, 6-sided die, what is the probability of rolling a number other than 6? Let's break this down step by step, just like we did in the previous example. First, we need to identify our event, which we'll call E in this case. Let's define event E as the specific outcome of rolling a 6. Next, we calculate the probability of that event occurring, written as P of E since a standard die has 6 sides and only one of those sides is a 6. The probability of E is 1 over 6. Now we identify the complement, which we denote as E bar. Remember from our earlier slides, the complement is simply the event, not E, so E bar represents the event of rolling any number except 6, which would be rolling a 1, 2, 3, 4, or 5. To find the answer, we apply the fundamental formula we learned on slide 3. P of E bar equals 1 minus P of E. Substituting our known value into the formula, we get P of E bar equals 1 minus 1 over 6. To solve this, we find a common denominator, which gives us 6 over 6 minus 1 over 6. This leaves us with 5 over 6. Therefore, the final probability of rolling a number other than 6 is 5 over 6. As we move to the next slide, keep in mind that while this calculation seems straightforward, there are a few common pitfalls to watch out for when dealing with more complex outcomes. Common mistakes to avoid. First, let's talk about a common conceptual error: confusing a complement with an opposite in events with multiple outcomes. I often see students think that if an experiment has 3 possible outcomes, let's call them A, B, and C, then the complement of a must be B. This is a mistake. Remember what we learned on slide 2. The complement is simply not A, so if you are looking for the complement of A, you must include every other possibility that isn't A in this case. The complement of A would actually be the combination of both B and C. Next, watch out for incorrect summation. This is a great way to check your work. As we saw in our mathematical relationship on slide 3, the probability of an event plus the probability of its complement must always equal exactly 1. If you finish a problem and find that your 2 probabilities sum to more than 1 or less than 1, stop immediately. It is a clear signal that a calculation error has occurred. Finally, be careful with your notation. It is easy to get sloppy when writing quickly. Make sure you clearly distinguish between E, which represents the event itself, and P of E, which represents the numerical probability of that event occurring. Keeping these distinct will help you avoid confusion when you start applying these formulas to more complex problems. Now, before we wrap up with our final summary, I want to pause and discuss some common pitfalls. Even when you understand the formulas we discussed earlier, it is very easy to fall into certain traps. Now, let's move to our final slide to consolidate everything we have learned today. Key takeaways. First, remember that the complement of an event, which we call E, is simply the event E bar, which represents the event that E does not occur. Second, it is crucial to understand that an event and its complement are both mutually exclusive and exhaustive. This means they cannot happen at the same time, but together, they cover every single possible outcome in our experiment. Third, because they cover all possibilities, the sum of the probability of event E and the probability of E bar must always equal 1. Mathematically, we express this as the probability of E plus the probability of E bar equals 1. Finally, keep this practical tip in mind. The formula where the probability of E bar equals 1 minus the probability of E is an incredibly powerful tool. You will find it especially useful when you encounter probability problems that ask for at least one or scenarios involving not something happening. It can often save you a lot of complex calculations. All right, we have reached the end of our lesson, so let's wrap everything up by reviewing the key takeaways from today's session. That concludes our lesson on complementary events. Great job staying focused.